Hello. So I've assigned chapter 20, problem 36, and this problem just asks us to review the conceptual example number 7 as an aid in solving this problem. So I'm just going to go over that really quick. There are extension cords and a potential fire hazard. So this problem just talks about how during the winter time, many people use portable electric space heaters to keep warm. And whenever the heater is located far from a 12-volt wall receptacle, an extension cord is necessary. So to prevent fires, however, manufacturers sometimes caution about using extension cords to minimize the risk of a fire. Should a long extension cord used with a space heater be made from a larger gauge or a smaller gauge wire? So here's just the image that we can look at while thinking about this problem. And just so we know, they decided that a smaller gauge wire is the correct thing to use. Since the wire's resistance depends inversely on its cross-sectional area, a smaller gauge wire with its larger cross-sectional area has a smaller resistance. So the smaller resistance would lead to a less heating of the extension cord due to the power RMS times R extension cord dissipated in it, thus minimizing the risk of a fire. So the problem reads that a portable electric heater uses 18 amps of current, and the manufacturer recommends that an extension cord attached to the heater receive more than 2.0 watts of power per meter of length. What is the smallest radius of the copper wire that can be used in the extension cord? Note, an extension cord contains 2 wires. Although the human eye just sees there's one wire, the physics behind the cord is that there are 2 wires within it. So we're given our current, and then we also have our Pmax. So they want us to find the smallest radius of the copper wire. So this problem derives from section 5, alternating current. So within the chapter, we learned that R is equal to rho times L over A. So that's a very important formula because with area, we can find the radius. And we all know that area is equal to pi r squared. So we can take this formula and manipulate it. A equals PL over R, and manipulate it to rho current squared over PL. So since the area is equal to R pi squared, we change the formula into this form. R equals the current times the square root, which comes from the square of pi within the area formula, over pi times P over L. So we just plug in the numbers, and the current is 18 times the square root of rho over pi P over L. And so rho is a coefficient, and that number is 1.72 times 10 to the negative 8 ohms times meters over pi times 2.0 watts per meters. So after doing all of the math, we have that the radius, excuse this marking right here, but the radius, this should be radius, is equal to 0.000942, which we then round to 9.42 times 10 to the negative 4 meters. So that's how we find the smallest radius of the copper wire. Notice that we've used the 2.0 watts for the max because that just allows us to know, what the maximum power per unit length is that the extension cord itself can produce. So that just gives us our final answer right here. All right, thank you.